Hello, everyone, and welcome to another wonderful day of Crash Course Spectroscopy. So, today we're going to be focusing in on rotational spectroscopy. However, before we really focus in on the spectroscopy component, what we really should do is go ahead and review our good old rotational energies. So, this takes us way back, all the way to our first principles of quantum mechanics. I believe that was chapter 7. And so one of the first things we need to be looking at is the energy levels for rotational motion, because what we're really going to be looking at with spectroscopy is going to be the difference in these rotational energy levels. So the typical approach for this is going to be looking at molecules that can rotate across several axes. So be it X, Y, or Z. So a good approach is going to be trying to solve for each of these axes individually and then combine the net answer. So when we go ahead and do this, the energy for any given axis, so axis here is going to be Q, so this could be X, is going to be equal to 1/2 the moment of inertia times the rotational frequency. So again, our moment of inertia is going to be a measure of both how heavy an object is and how far away from it is from the center of rotation. The further away it is, the harder it is going to be to move. So anybody who's sitting way out far from the axes is going to count more. And our omega here is again going to be the rate of rotation in radians per second. So again, here my Q can be any of my axes, X, Y, or Z. And a lot of our trick here is going to be focusing in on how to solve for the moment of inertia, which turns out to be largely uh, an issue of geometry, and it can actually be quite messy. So we did this previously for diatomics, and it wasn't too bad. But as we get to polyatomic species, it gets a little bit tricky. So my moment of inertia for, say again, axis Q is going to be the sum of each of the atoms, the mass of each of these atoms, times the distance of the atom away from the axis. So if I have systems like atoms B and C who sit on the rotational axis, they don't count at all because I don't actually have to move them. Atoms like uh, the A set is actually going to have a decent effect because they will have some mass and they will be some distance away. But the atoms, the D set of atoms, who are much further away, are going to count a lot more. And you'll essentially have one count for each of the individual atoms, not just atom types. So if I've got 3 atoms circling, they'll count 3 times. And again, you're going to need to repeat this process for each of the relevant axes. So here, Q can be the distance from the x-axis, the distance from the y-axis, and the distance from the z-axis. Each one will give you one of your 3 different moments of inertia. So once we have our moments of inertia, we can then go ahead and plug those into our energy equations and add up all of the energies in each axis. So my total energy is going to be related to the energy of rotation in x, y, and z. Now it is important to note if one of the moments of inertia is going to be 0, say all the atoms lie on the axis, then that energy term from that direction will simply just drop to 0, which is actually fairly convenient for our sake. Now, one of the things that we have seen before is that we typically don't like to work in velocities. Instead, it's a very PChem thing to do to work in momenta space. So instead of using the rotational velocities, we're going to use the angular momentum, which again, as a reminder, can simply be given by the rotational velocity times the moment of inertia. So with some rearrangement, we get our old friend. The energy is equal to the angular momenta squared over twice the moment of inertia. So we did use this one again when we were working with simple rotational systems. We're just now scaling it up to a three-dimensional component because we're no longer guaranteed that my moments of inertia will be equal in any given direction. So as you may note, one of our large tricks is going to be trying to develop these moment of inertia terms for more complicated molecules. So for a diatomic molecule, this is our good old friend, where our moment of inertia is going to be equal to uh, the effective mass of the system times the radius or the bond length squared. So this was our good friend. Total effective mass is the two masses multiplied by each other divided by the total mass. So this one wasn't too bad. It's also logically isn't too bad to try and extend this to a triatomic system where we end up simply having to bring in an extra mass. So this actually ends up being pretty easy if both of my edge atoms are the same identity, because my atom B in this case, my central atom, will lie exactly on the axis of rotation because my A atoms will be rotating about atom B. So it won't contribute anything to the moment of inertia, and the moment of inertia will simply be twice the mass of the rotating atom times the bond length, because that's again going to be the distance of this atom from the center of mass. Now things get a little bit more messy if atoms A and C, my two N atoms, let's call them A and C, are different. Because under this context, I don't know exactly where my center of mass lies. And the center of mass will end up moving depending on the ratio of these masses. So what we need to do is essentially, we'll start with the same idea that my moment of inertia is going to be related to the mass of both of my atoms times the respective distance from my central atom. But then I need to introduce a term that shifts the center of mass away from my center. So it turns out that if the masses and lengths are very similar, then these terms will cancel out and I'll get my original homonuclear system back. However, the more different these masses and bond lengths are, the more I'm going to essentially shift my center of mass till you get to something like HCN, where the center of mass lies more in between the carbon and nitrogen bond than it is to the carbon atom itself. Then we end up also dealing with what we call spherical systems. So these are our classic linear rotors, and these are going to be our spherical systems, where for our linear molecules, I really only have one moment of inertia, so that would be along, let's call it axis A, because along axis Y, it turns out there's no rotation at all because everybody lies on the axis. So that ends up helping simplify these terms. However, for spherical systems, we run into a slight complication because they can rotate in all three dimensions. But what makes spherical systems so wonderful and unique is that the moment of inertia is going to be equal for all three inertias. So Ix equals Iy equals Iz. And so again, if I'm dealing with a tetrahedral system, so 4 atoms on the edge, it turns out that we can that my central atom will be the center of mass. So it doesn't actually matter what the identity of our central atom is at all. Instead, the moment of inertia will entirely depend upon the mass of the exterior atom and its distance. However, you might be wondering where this 8/3 comes from. And the answer is essentially geometry, because what ends up happening is that effectively not all of the mass is evenly distributed along the rotor, and it's essentially going to be shifted based on the bond angle. However, if I have a tetrahedral system, this angle is 109, and I can make the I can make the geometry work to actually help figure out the distance of this atom from the central axis. So again, it becomes a little bit more complicated argument of geometry at that point. However, if we are dealing with an octahedral system, so this is our classic TD symmetry, or sorry, OH symmetry. Sorry, this is TD symmetry. If we have a classic OH symmetry around a simple central atom, this actually is quite a nice case because we have essentially three axes of rotation. One along this set of bonds, one along this set of bonds, and one essentially rotating in the plane. All three of them are equal and will all have an identical moment of inertia. And solving each one is actually quite easy, as I'm going to have four masses on the outside. So I'm just going to add them up where it's the mass of the atom times the square of the distance. So again, a nice, easy case to solve. So we love our spherical systems. And one of the reasons why we love our spherical systems is because they make our energy expression quite nice, as all of my moments of inertia collapse down to a single denominator, which then lets me add together my individual component angular momentums, which, as you may recognize, gives me my an energy that's the total angular momentum squared over twice the moment of inertia. So this is more or less the exact same answer we previously derived for a diatomic molecule. We love it when it's nice and straightforward. However, and I apologize for the notational difficulties, it turns out we don't actually like using the total angular momentum. Instead, we like using angular momentum quantum numbers. So specifically, we tend to use the total angular momentum quantum number, which has the same exact symbol of J. I am so sorry. But as a reminder, the value for the total angular momentum and the quantum number are going to be related by h bar squared times the quantum number plus 1. So again, if I have a value of 0, I am in my ground state rotation. The whole thing goes down to 0. If I have a value of 1, then this whole term goes to 2, and my energy is h bar squared over I. So, old friend, but it's been a good long while. So this is what this is the expression we use to determine the energy of any given rotational state. So for any particular value of the quantum number, ranging from 0 to essentially infinity, as long as it's an integer value. However, we are now in spectroscopy land, so it turns out we like expressing the energy more in terms of a wave number convention. So what we do is we tend to grab all of my prefactors here, this h bar squared over 2i, put it into wave numbers, and then can turn this into our rotational constant. So this is our B tilde. This is going to be showing up periodically throughout the rest of the chapter. And so we can now express our energy as hc, so this is the conversion from wave numbers to energy, times our constant times j plus 1. And so what this ends up effectively looking like in terms of energy spacing is, at very small j values, our energies are going to be very tightly packed. And as our j values start increasing, I start to go to higher and higher rotational states. My energies will start spreading out quite a lot. And so, again, being spectroscopy, they often are a little bit less concerned about energy levels, like me, the humble quantum guy I am, and they care about much more about the energy as expressed again in terms of wave numbers, at which point all that we really do is we drop the HC term and we get our what they call the rotational term, which is more or less just the energy in terms of wave numbers. However, This is spectroscopy, so we care very little actually about the energy states, and what we care much more is about the energy separations, or what wavelength or wave number of light is going to allow an excitation. So if I'm looking at adjacent states, the separation energy can simply be given by my initial state, Fj, and my final state, Fj plus 1. So then we can put in values, put in a value of j for this term, and then we'll plug in j plus 1 for this expression. And we do this, so we have our initial state here, and our final state is essentially the rotational constant times j plus 1 times j plus 2. So j plus 1 goes in here, j plus 2, that's our second term. Now, this is quite an ugly little expression. We FOIL out some terms, do some simplification, and it turns out that the separation energy can be expressed in terms of twice the rotational constant times my initial state, so the one I'm being excited out of, plus 1. So this means that if I'm excited from the ground state to the first rotational state, this will have a peak at twice the rotational constant, and then we'll see that value go up systematically as I walk through my rotational states. And so this is really what we're going to be looking for. Again, this will tend to show up in the microwave region. Now, this was, again, all assuming a spherical molecule. We can adapt this slightly for a linear molecule. Big difference, again, for a linear molecule is only a single direction, has a non-zero value for the angular momentum, which essentially is going to end up making sure that our other directions of rotation drop down to 0. And so what ends up happening, if you walk through the math, is it produces, again, a single rotational quantum number. But functionally, our equation doesn't change. Because now, since the x and y directions completely dropped out, my total angular momentum was entirely the angular momentum in that z direction. So that also became j squared. So if you want to, feel free to walk through the mathematics. But it is actually fairly useful that no matter what type of linear or spherical molecule I am working with, I will always be able to depict my energy levels with the same general expression. Though again, the moments of inertia will slightly differ in between the systems. However, it turns out that the major difference is because I have fewer directions I can spin, the degeneracy of my energy levels will change. So again, we proved this earlier in the semester, but the degeneracy of energy levels for a linear rotator are essentially 2j plus 1. Essentially, this will be dictated by how many directions I can move, whether I'm moving with a value of whether my total angular momentum will max out in either the positive or the negative direction. But even if I have a j of 0, I'll always have at least one rotational energy allowed, which essentially is nothing that's measurable. However, this does actually change when we go to the spherical rotor, where it turns out we have 2j plus 1 squared degenerate levels. So we'll have essentially the square of the number of degenerate levels that I have for a linear rotor. And when this actually comes into major play is with the intensity of signals. Because remember that one of the things that dictates the intensity of signals is how many molecules are in any given state. So for a linear system, I have rather fewer hot energy levels for high I have a rather lower degeneracy for high rotational energy levels, so that there will be fewer molecules in these elevated states. However, when we go to more complicated molecules, as the degeneracy goes up, the number of molecules that will occupy those states will also increase. So I'll have a much greater intensity of signals from high J values when I'm looking at microwave excitations. And we'll see this as we go on and look more explicitly at rotational spectra that will typically have very low intensity for J values of 0 or 1, and then they'll max out at some intermediate level and then drop down as the energy separation essentially dominates this higher degeneracy term. However, one of the other things we need to actually examine for rotational systems is going to be selection rules. Because again, it turns out that we can't actually excite from any rotational state to any rotational state. So the first general rule that applies to rotational spectroscopy is that in order for a molecule to absorb a photon, it must possess a dipole. And so one way to look at this is that, again, a molecule must be able to change polarization upon absorption of a photon. This was our general selection rule. Now, what ends up happening is that if I have a dipole and I absorb a photon, I'm going to essentially increase the rate of that dipole change. However, if these two ends are equal and I increase the rotation, congratulations. If you speed up a nonpolar molecule, you still end up with a nonpolar molecule. If you speed up a slightly polar molecule, you're essentially going to increase the amount of charges, effective charge on the ends. And that's really what we're looking at. However, it also turns out that by applying the mathematical transition dipole moment operator, we can narrow this down a little bit more by conservation of angular momentum. And it turns out that our J value can only increase or decrease by 1 upon emission of a photon. Absorption of a photon. However, if I'm looking at the microwave region, we still have to account for conservation of energy. So if energy comes in upon absorption of a photon, the only way I can go is up. And if I emit a photon, the only way I can go is down. Now, this leads our general selection rule of that if I am absorbing a photon, my rotational state has to change by 1, but it turns out that my direction can either stay, the angular momentum in the z direction can either stay the same, increase, or decrease by 1. So if I already have a negative m sub j, it's probably just going to get larger if I absorb a photon. If I have a positive m sub j, it's probably either going to get larger if I absorb a photon. But if my angular momentum increases in some other direction, then I won't see any effect in my net magnetism or angular momentum in the j direction. One of the things that is a slight exception to this is that it turns out that if I'm looking at a relaxation, however, it is going to be possible for our J value to stay constant if I have a relaxation of rotation of. It is possible for my J to not change if I have my molecule relax in some other direction, specifically if I have involvement of electronic energy. But one of the most frequent things that we may end up having is that if I have a relaxation of my higher energy vibrational spectra, it turns out that my rotational value can still go down because I will have relaxed that conservation of energy. So this brings us to the end of rather simple rotational spectra looking at linear and spherical molecules. However, it turns out that not everything is going to be so geometrically simple. So next time, we're going to be looking at slightly more complicated molecules. Till then, take care, stay healthy.